Hey everyone, and welcome back to the channel. Today, we're tackling one of the most fascinating and widely repeated claims in all of planetary science. Is the moon really protecting Earth? You've probably heard this dozens of times, that our lunar companion acts as a cosmic shield, defending us from asteroids, stabilizing our climate, and making life on Earth possible. It's a beautiful idea, almost poetic. But how much of this is solid scientific fact? And how much is exaggeration or oversimplification? Over the next hour, we're going to dive deep into the moon's role in Earth's story. We'll explore the dramatic and violent origin of our satellite, examine each protective claim with real data and current research, and discover some surprising truths about what life on Earth might be like without the moon hovering above us. I can promise you that some of what we'll uncover might challenge what you thought you knew. The reality is more nuanced and, in many ways, more interesting than the simplified story we often hear. This isn't just about debunking myths. It's about understanding the genuine, complex relationship between Earth and its only natural satellite. A relationship that has been evolving for 4.5 billion years and will continue for billions more. We'll look at cutting-edge research, explore alternative scenarios, and try to answer the fundamental question: is Earth's habitability truly dependent on the moon, or could life have flourished here regardless? So grab your favorite beverage, settle in, and let's embark on this lunar journey together. By the end, you'll have a much deeper appreciation for both what the moon does for us and what it doesn't. Before we can understand what the moon does for Earth today, we need to understand where it came from and how it got here. The origin story of the moon is one of the most dramatic and violent events in our planet's history. And it's a story that scientists have only pieced together relatively recently. About 4.5 billion years ago, when Earth was just a cosmic infant, barely 50 to 100 million years old, something catastrophic happened that would change the destiny of our planet forever. Picture this. Our young Earth was still largely molten, still being bombarded by debris left over from the formation of the solar system. It had barely begun to cool. And then, a Mars-sized protoplanet came barreling through space on a collision course with our world. Scientists have named this hypothetical planet Theia, after the Greek Titan, who was the mother of Selene, the moon goddess. Theia was massive, roughly 10% of Earth's mass, about the size of Mars. When I say it collided with Earth, I'm not talking about a glancing blow or a gentle merger. This was a catastrophic impact at speeds of several kilometers per second, with an oblique angle that made the collision even more violent. Try to imagine the sheer magnitude of this event. The energy released was almost incomprehensible, equivalent to billions of nuclear weapons detonating simultaneously. Temperatures at the impact site soared to tens of thousands of degrees Celsius. Rock didn't just melt. It vaporized instantly. The shockwave from the impact rippled through Earth's entire body, potentially melting much of our planet's mantle. For a brief, terrifying moment, Earth effectively had a massive wound, with a geyser of vaporized rock shooting thousands of kilometers into space. Both Theia and a significant portion of Earth's outer layers were essentially destroyed in this collision. Most of Theia's iron core, along with much of Earth's core, sank to the center of our planet due to their higher density. But the lighter, rocky material from both worlds' mantles was blasted into orbit around Earth as a cloud of vaporized and molten debris. The entire surface of Earth became an ocean of magma, glowing red-hot and radiating enormous amounts of heat into space. Now, here's where the story becomes even more remarkable. This ring of debris orbiting Earth didn't just stay scattered. Within perhaps just a few thousand to a few million years, an eye blink in geological terms, the debris began to coalesce under its own gravity. Larger chunks attracted smaller ones. Gradually, through countless collisions and mergers, the moon formed from this ring of destruction. The moon was born from violence, a phoenix rising from the ashes of a planetary collision. This theory, known as the giant impact hypothesis, wasn't always the accepted explanation. For a long time, scientists debated three main theories: that the moon formed alongside Earth from the same disk of material, the co-formation theory; that Earth's gravity captured a passing body, the capture theory; or that Earth spun so fast a chunk flew off the fission theory. But each of these had serious problems. The giant impact hypothesis, first proposed in the 1970 seconds and refined ever since, has become the leading explanation because it explains so many puzzling features of the moon that the other theories couldn't. For instance, it explains why the moon has a relatively small iron core compared to Earth. Most of Thea's core and much of Earth's core merged together during the impact, while the moon formed primarily from mantle material. It explains why moon rocks brought back by Apollo astronauts have similar isotopic compositions to Earth rocks. They literally came from the same collision, a mixture of Earth and Theia. And it explains why the moon is so large relative to Earth, compared to most other planet-moon systems in our solar system. At about 27% of Earth's diameter, the moon is by far the largest satellite relative to its planet among the terrestrial worlds. But here's what's absolutely crucial for our story today. This violent birth didn't just create the moon. It fundamentally changed Earth's destiny and established a relationship that has been evolving ever since. When the moon first formed, it was incredibly close to Earth, perhaps just 15,000 to 20,000 kilometers away, compared to the 384,000 kilometers that separate us today. At that distance, if you could stand on the primordial Earth and look up, assuming you could survive the hellish conditions, the moon would have appeared absolutely enormous in the sky, perhaps 15 to 20 times larger than it appears today. It would have dominated the heavens, looming overhead like a vast, cratered world. At this close distance, the tidal forces between Earth and moon were immensely powerful. The moon's gravity raised enormous tides in Earth's magma ocean, creating bulges hundreds of meters high. But tides work both ways. Earth's much stronger gravity was also pulling on the young moon, flexing and heating it. The moon was probably also molten or semi-molten for a considerable period, with a magma ocean of its own. These strong tidal interactions had two major, lasting effects that continue to this day. First, they began to slow Earth's rotation. When the moon formed, Earth was spinning much faster than it does now. A day on the newly formed Earth was probably only 6 to 8 hours long, just a quarter of our current 24-hour day. The tidal friction between Earth and the bulges raised in its oceans and crust acted as a brake, gradually slowing our planet's spin over billions of years. Second, the same tidal interaction transferred angular momentum from Earth's rotation to the moon's orbit. This caused the moon to gradually spiral outward, moving farther from Earth with each passing year. This process continues today. Scientists can measure it precisely using laser reflectors left on the moon by Apollo astronauts. The moon is currently receding from Earth at about 3.8 centimeters per year, roughly the same rate your fingernails grow. This means that in the past, the moon was closer and appeared larger in the sky, while days were shorter. In the future, the moon will be farther away, appear smaller, and days will be longer. The Earth-Moon system is not static. It's a dynamic, evolving relationship that has been changing since the moment of the moon's birth. From that dramatic beginning, Earth and moon have been locked in a gravitational dance, each shaping the other in profound ways. Now, let's examine what that relationship means for Earth's habitability. Let's tackle the most popular and widely repeated claim about lunar protection. The idea that the moon shields Earth from asteroid impacts. You've almost certainly encountered this idea. It's in documentaries, science articles, and countless YouTube videos. The moon, we're told, acts as Earth's bodyguard, taking hits that would otherwise strike our planet and potentially cause mass extinctions. It's a compelling and dramatic image, and there's definitely a grain of truth to it. But the reality is far more nuanced and much less dramatic than most people realize. Let's dig into the actual science. First, let's look at the evidence that initially supports this idea. Look at any detailed photograph of the moon, and you'll see that its surface is absolutely covered in craters. Unlike Earth, the moon has no atmosphere to burn up incoming objects, and no geological activity, no plate tectonics, no volcanism, no erosion to erase impact scars. The moon is essentially a 4 billion-year archive of cosmic collisions, preserving a record that has been largely erased on Earth. Some of these lunar impacts have been truly massive. The South Pole Aitken Basin, located on the moon's far side, is one of the largest impact craters in the entire solar system. It stretches about 2,500 kilometers across and penetrates up to 8 kilometers deep. The asteroid or comet that created this basin must have been enormous, perhaps 200 kilometers in diameter. If such an object hit Earth today, it would be a civilization-ending event, possibly even threatening our survival as a species. The more recent Tycho crater, created just 108 million years ago when dinosaurs walked the Earth, is another impressive example. The impact was powerful enough to eject bright rays of material across thousands of kilometers of lunar surface. You can see these rays with binoculars. The asteroid that created Tycho was probably about 10 kilometers across. For comparison, the asteroid that helped kill the dinosaurs 66 million years ago was about the same size. So yes, the moon clearly intercepts objects. Some of these would have been dangerous to Earth. Case closed, right? Not quite. Here's where we need to do some careful thinking and math. The critical question isn't whether the moon blocks any asteroids, it obviously does, but rather, what percentage of Earth-threatening asteroids it actually prevents from hitting us. Let's think about this geometrically. The moon's cross-sectional area, the target it presents to incoming objects, is about 38 million square kilometers. That might sound huge, but Earth's cross-sectional area is about 127 million square kilometers. Earth is roughly 3.7 times larger as a target. Already, we can see that Earth is much more likely to be hit simply because it's bigger, but size isn't the only factor. We also need to consider orbital geometry. The moon orbits at an average distance of 384,000 kilometers from Earth. From the perspective of an asteroid approaching from deep space, say, from the asteroid belt between Mars and Jupiter, the moon and Earth appear relatively close together, but the moon only blocks a tiny fraction of the possible approach angles. Think of it this way. Imagine you're throwing darts at a dartboard from across a room. Now imagine placing a small coin somewhere near the dartboard. The coin might block an occasional dart, but most darts headed for the dartboard will still hit it. The moon is like that coin, it's in the general vicinity of Earth, but it only blocks a small fraction of the darts coming our way. Planetary scientists have run detailed calculations and simulations on this question. The consensus is that the moon intercepts somewhere between 1% and 2% of objects that might otherwise have hit Earth. Let me emphasize that. 1 to 2%. That's not nothing over billions of years. That's probably hundreds of thousands of impacts that Earth avoided. But it's a far cry from the impenetrable shield many people imagine. To put this in perspective, If 100 asteroids were on a collision course with Earth, the Moon would block 1 or 2 of them. The other 98 or 99 would still hit Earth. The Moon is providing a small statistical benefit, not a comprehensive defense system. But wait, there's more to consider. The Moon doesn't just passively sit there blocking objects like a wall. It has gravity, and gravity affects the trajectories of passing objects. This creates 2 competing effects. On one hand, the Moon's gravity can deflect some objects that are passing nearby, potentially saving Earth from impacts. An asteroid that might have grazed Earth could get its path bent by the Moon's gravity, causing it to miss our planet entirely. This is called gravitational scattering, and it does happen. On the other hand, and this is what people often forget, the Moon's gravity can also focus objects toward Earth in certain orbital configurations. Depending on the geometry, the Moon's gravity can actually increase the probability that a nearby object will hit Earth. It can pull objects toward the Earth-Moon system that might otherwise have passed harmlessly by. The net effect of these competing influences is complex and depends on many factors: the size and speed of the object, its approach angle, and the Moon's position in its orbit. Scientists have studied this using computer simulations, and the consensus is that these gravitational effects roughly balance out. The Moon's gravity helps us about as often as it hurts us. Now let's talk about something that provides far more protection than the Moon ever could: Earth's atmosphere. Earth is surrounded by a substantial atmosphere that extends hundreds of kilometers above the surface. This atmosphere is an incredibly effective shield against small and medium-sized objects. Any object smaller than about 25 meters in diameter will typically burn up completely in the atmosphere, never reaching the ground. The friction with air molecules heats these objects to thousands of degrees, vaporizing them in a brilliant meteor streak. Even larger objects get broken up and slowed down by the atmosphere. The famous Chelyabinsk meteor that exploded over Russia in 2013 was about 20 meters across near the threshold size. It exploded in an airburst that shattered windows and injured over 1,000 people. But it didn't create an impact crater. The atmosphere destroyed it before it could reach the ground. The vast majority of objects that actually threaten Earth are relatively small in the 10 to 100 meter range. The atmosphere handles most of these. The objects large enough to survive atmospheric entry and cause serious damage are much rarer. A 1-kilometer asteroid hits Earth only about once every 500,000 years on average. A 10-kilometer asteroid, the dinosaur killer size, hits roughly once every 100 million years. The Moon, with no atmosphere, is far more vulnerable to small impacts. Every tiny meteoroid that would burn up harmlessly in Earth's atmosphere creates a crater on the Moon. This is why the Moon is so heavily cratered, while Earth's surface is relatively smooth. The Moon's cratered appearance is actually evidence that it has less protection than Earth, not more. Let me give you another perspective. Jupiter is sometimes called the vacuum cleaner of the solar system because its enormous gravity does deflect or capture some objects that might otherwise enter the inner solar system. Jupiter's protective effect is much more significant than the Moon's, perhaps reducing Earth's impact rate by 10% to 20%. Yet even Jupiter doesn't prevent most impacts. There's also a historical consideration. Earth has been hit by massive asteroids many times in its history, despite having the Moon. The dinosaur extinction 66 million years ago, the late heavy bombardment around 4 billion years ago, and numerous other impact events all occurred with the Moon orbiting overhead. The Moon didn't prevent these catastrophes. Here's an interesting thought experiment. If the Moon were twice as large, it would block maybe 4% of asteroids instead of 2%. If it were 5 times larger, maybe 10%. Even a Moon substantially larger than ours would not provide comprehensive protection. The only way the moon could truly shield Earth would be if it were comparable to Earth in size and orbited very close. But then, it wouldn't really be a moon anymore, and the tidal forces would be catastrophic. So what's the verdict on the asteroid shield claim? The moon does intercept some potential impactors, that's undeniable. Over billions of years, it has probably blocked thousands of impacts that would have otherwise struck Earth. Some of these might have been significant. In that limited sense, the moon does provide some protection. But calling the moon Earth's asteroid shield is a significant overstatement. It's more accurate to say that the moon provides a small statistical reduction in impact probability, blocking perhaps 1 to 2% of potential impactors. Earth's atmosphere provides far more protection against the smaller, more common objects. And for the rare, civilization-threatening asteroids, the moon offers minimal defense. The asteroid shield myth is a good example of how scientific ideas can get oversimplified as they spread through popular culture. The kernel of truth, the moon does block some asteroids, gets amplified into a more dramatic claim that doesn't match the actual science. Now, let's turn to something the moon definitely, unquestionably does influence in a major way: Earth's tides. This is where the moon's impact on our planet becomes more substantial and interesting. The story of tides is a story about how cosmic forces shape not just water, but life itself. Everyone learns in school that the moon causes tides. But the full story is more fascinating than most people realize. And it has implications that go far beyond water sloshing up and down on beaches. Let's start with the basics of how tides actually work. The moon's gravity pulls on Earth. But here's the key insight: it doesn't pull uniformly. The side of Earth facing the moon experiences slightly stronger gravitational pull than Earth's center, which in turn experiences stronger pull than the side facing away from the moon. This difference in gravitational force across Earth's diameter is called a tidal force. These tidal forces create bulges in Earth's oceans. There's a bulge on the side facing the moon, which makes intuitive sense. The moon is pulling water toward it. But here's what surprises many people. There's also a bulge on the opposite side of Earth, on the side facing away from the moon. Why? The reason is subtle but important. Earth itself is being pulled toward the moon more strongly than the water on the far side. Imagine it this way. The moon pulls the solid Earth away from the water on the far side, effectively leaving that water behind. The result is bulges on both sides of Earth, one where water is pulled toward the moon, and one where Earth is pulled away from water. Now, Earth rotates through these two bulges, spinning underneath them. As any given point on Earth's surface rotates through the bulge facing the moon, it experiences high tide. About 6 hours later, that point has rotated 90 degrees and is between the two bulges, experiencing low tide. 6 hours after that, it's rotated through the far side bulge, experiencing high tide again. This is why most coastal areas experience 2 high tides and 2 low tides approximately every 24 hours and 50 minutes. The extra 50 minutes accounts for the moon's orbital motion. But the moon isn't the only body creating tides. The sun also creates tides, and they're actually quite substantial, about 46% as strong as the moon's tides. This surprises many people. The sun is enormously more massive than the moon, but it's also enormously farther away, and tidal force decreases very rapidly with distance. It follows an inverse cube law, not just inverse square. The interaction between solar and lunar tides creates the familiar pattern of spring tides and neap tides. When the sun, moon, and Earth align during new and full moons, the solar and lunar tides add together, creating spring tides, the highest high tides and lowest low tides of the month. When the sun and moon are at right angles during quarter moons, their tides partially cancel each other out, creating neap tides more moderate variations. Now, these tides do far more than just move water up and down beaches. They're a powerful force shaping coastal ecosystems and, quite possibly, the evolution of life itself. Tides create intertidal zones, regions of the coast that are alternately submerged underwater at high tide and exposed to air at low tide. These zones are incredibly challenging environments. Organisms living there must be able to survive both underwater and in air, must cope with dramatic temperature swings, must handle the pounding of waves and the drying effect of sun and wind. Yet, despite these challenges, or perhaps because of them, intertidal zones are among the most productive and diverse ecosystems on Earth. Walk along any rocky coast at low tide, and you'll find a world of life. Barnacles clinging to rocks, sea anemones waiting in tide pools for the water to return, crabs scuttling between crevices, mussels clustering in dense beds, starfish hunting for prey, seaweeds of every color and form. Each organism has evolved remarkable adaptations to this harsh, fluctuating environment. Barnacles cement themselves to rocks and close their shells tight during low tide, then open up to filter feed when the water returns. Sea anemones can retract their tentacles and become dormant blobs during exposure to air. Mussels can seal their shells and survive for hours without water. The adaptations are endless and ingenious. But intertidal zones may have played an even more fundamental role in the history of life on Earth. Some scientists have speculated that tidal pools might have been crucial to the origin of life itself, or at least to major transitions in life's evolution. Here's the idea. Tidal pools concentrate organic molecules as they evaporate during low tide. This concentration effect could have accelerated the chemical reactions that led to the first self-replicating molecules, the dawn of life. When the tide comes in, new organic molecules from the ocean would be delivered to the pools. When it goes out, the concentration process begins again. This cycling could have provided exactly the kind of chemical environment needed for life's origin. Now, this is still speculative. We don't know for certain where or how life began. But tidal pools remain one plausible candidate for life's birthplace, and their existence depends on tides. Perhaps more importantly, tidal zones almost certainly played a crucial role in one of life's greatest transitions: the move from water to land. About 375 million years ago, during the Devonian period, some fish began to venture onto land. This was one of the most momentous events in the history of life, because it eventually led to all terrestrial vertebrates, amphibians, reptiles, birds, mammals, and ultimately us. The fossil Tiktaalik, discovered in 2004 inches Arctic Canada, beautifully illustrates this transition. Tiktaalik had both fish and tetrapod characteristics. It had gills and scales like a fish, but it also had primitive lungs that could breathe air, a flexible neck, and sturdy fins with bones that could support its weight. It could live in shallow water and probably venture onto mudflats. Why would any fish start coming onto land? Land was a harsh, alien environment for creatures that had evolved in water for hundreds of millions of years. But the intertidal zone provided a bridge, a place where organisms were forced to adapt to both water and air. Tidal pools left behind at low tide might trap fish, forcing them to either develop the ability to survive brief periods in air or die. Over millions of years, natural selection favored individuals with lungs, stronger fins, and other adaptations for surviving and eventually exploiting terrestrial environments. The rhythmic nature of tides also synchronized biological processes. Many marine organisms time their reproductive cycles to tidal and lunar cycles. Corals in many species engage in mass spawning events triggered by lunar phases, releasing eggs and sperm simultaneously to maximize fertilization. Grunion fish in California famously ride waves onto beaches during spring high tides to lay their eggs in the sand, where they develop for 2 weeks before the next spring tide washes them back to sea. Countless other species use tidal and lunar cues to coordinate their behavior. Tides also drive massive ecological processes. Tidal currents mix and circulate nutrients, carrying them from shallow coastal areas to deeper waters and back. This nutrient mixing supports the productivity of coastal oceans, which are among the most biologically rich areas of the marine environment. In some regions, tidal currents create upwellings that bring nutrient-rich deep water to the surface, supporting abundant life. So the moon's influence through tides is genuine and significant. But, and this is important, Earth would still have tides without the moon. They would just be weaker. Remember, the sun creates tides about 46% as strong as the moon's. Without the moon, we would still have solar tides. High tide would be less high, low tide would be less low. The difference between them would be less than half of what we experience today. But tidal zones would still exist. Tidal currents would still circulate nutrients, and evolution would still favor adaptations to changing water levels. Would life have moved onto land without lunar tides? Almost certainly yes. Solar tides alone would still create intertidal zones, though they'd be smaller. The transition might have taken longer or happened somewhat differently, but the fundamental selective pressure would still be there. Would life have originated in tidal pools without the moon? Possibly. Though, again, solar tidal pools would still exist, and tidal pools are just one hypothesis for life's origin. There are many other candidates, including deep-sea hydrothermal vents, which have nothing to do with tides at all. The moon has definitely enhanced tidal effects and may have accelerated certain evolutionary transitions. But it's hard to argue that tides and therefore life depend absolutely on the moon's existence. Solar tides would have created many of the same evolutionary pressures, just in a somewhat reduced form. Now we come to perhaps the most scientifically interesting and controversial claim about lunar protection. The idea that the moon stabilizes Earth's axial tilt, preventing chaotic climate variations that would make our planet uninhabitable. This claim has been repeated so often in documentaries, textbooks, and science articles that it has achieved the status of conventional wisdom. Many scientists accepted it for decades, but recent research has revealed a far more complicated picture. And the story of how our understanding evolved is a great example of how science progresses. Let's start by understanding what we're talking about. Earth's rotational axis, the line running through the North and South poles, is tilted about 23.5 degrees relative to Earth's orbital plane around the Sunday. This tilt is responsible for our seasons. During Northern Hemisphere summer, the North Pole is tilted toward the sun, bringing longer days and more direct sunlight to northern regions. 6 months later, the North Pole is tilted away, creating winter. Now, Earth's axis isn't perfectly stable. It wobbles slowly, like a spinning top, a phenomenon called axial precession, or precession of the equinoxes. This wobble has a period of about 26,000 years. Currently, Earth's north axis points roughly toward Polaris, the North Star. But 13,000 years ago, it pointed toward the star Vega. And 13,000 years in the future, it will point toward Vega again. There are also variations in the tilt itself, which oscillates between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. These variations, combined with changes in Earth's orbit, are part of what are called Milankovitch cycles. These cycles help explain the timing of ice ages over the past few million years. But compared to some other planets, Earth's axial variations are quite modest. This is where Mars enters our story. Mars is fascinating from a climatic perspective. Its axial tilt currently sits around 25 degrees, very similar to Earth's. But here's the shocking part. Computer simulations show that over millions of years, Mars's tilt has varied chaotically between about 10 degrees and 60 degrees, or even more in some scenarios. At 60 degrees, Mars would essentially be tilted on its side, with its poles pointing almost directly at the Sun during summer. Imagine what this would do to climate. At high obliquity, large axial tilt, Mars's poles would experience extreme seasons, months of continuous daylight in summer, with the Sun nearly overhead, followed by months of darkness in winter. Meanwhile, equatorial regions would become relatively cold because the Sun would never get very high in the sky. The climate would swing wildly between these different states over millions of years. Why is Mars so unstable? Mars has two small moons, Phobos and Deimos, but they're tiny, barely more than captured asteroids. They exert essentially no stabilizing influence. Mars also experiences strong gravitational tugs from Jupiter and Saturn. And these tugs, combined with Mars's own spin dynamics, cause its obliquity to vary chaotically over time. In 1993, a team of French scientists, including Jacques Lascar, published a landmark paper in the journal Nature that sent shockwaves through the planetary science community. They used computer simulations to model what Earth's obliquity would do without the Moon. Their result was startling. Without the Moon, Earth's tilt could vary between 0 and 85 degrees over billions of years. Think about what 85 degrees would mean. Earth would essentially be rolling around the Sun on its side, like Uranus, which has a 97-degree tilt. Each pole would spend half the year pointing almost directly at the Sun, experiencing months of continuous daylight with the Sun nearly overhead, followed by half a year of near total darkness. The temperature extremes would be enormous. At 0 degrees, no tilt at all, there would be no seasons. The Sun would stay at the same angle year-round at any given latitude. Polar regions would be permanently frozen, with the Sun always hugging the horizon. Equatorial regions might be scorching, with the Sun always nearly overhead. The climatic consequences of such dramatic shifts would be severe. Ecosystems adapted to moderate seasonal variations would be destroyed. Ice ages and greenhouse conditions would alternate in ways impossible to predict. The Lascar paper concluded that the Moon, by keeping Earth's obliquity relatively stable, varying only between 22 and 24.5 degrees, was essential for Earth's habitability and the evolution of complex life. This research led to a flood of popular science articles and documentaries declaring the Moon essential for life on Earth. It became one of the most frequently cited examples of lunar protection. For years, this was the accepted wisdom. But here's where things get interesting. Science is self-correcting, and as computational models improved and scientists examined the assumptions more carefully, doubts began to emerge. In 2011, a team including Jack Lissauer from NASA Ames Research Center published new simulations with improved models. Their results were surprising. Even without the Moon, Earth's obliquity would likely vary only between about 10 and 50 degrees, over billions of years, still more variable than our current situation, but nowhere near the catastrophic swings to 85 degrees that earlier models predicted. What was the difference? The earlier models had made simplifying assumptions about Earth's internal structure and rotational dynamics. Earth isn't a perfectly rigid body. It has liquid oceans, a molten outer core, and a mantle that can slowly deform. Earth also rotates fairly rapidly and has a relatively large moment of inertia, which provides inherent stability. When these factors were properly included in the models, Earth's obliquity became more stable. Additionally, the gravitational influence of other planets, particularly Jupiter and Saturn, affects Earth's axial behavior. The details of these interactions are incredibly complex and depend on precise orbital parameters. Small changes in assumptions can produce different outcomes. Subsequent studies have continued to refine our understanding. The current scientific consensus is that the Moon does provide some stabilizing influence on Earth's obliquity, reducing the magnitude of variations. But the effect is not as dramatic as once thought. And it's not clear that the Moon is absolutely essential for habitability. Furthermore, even if Earth's tilt did vary significantly, would that really prevent life? This brings us to an important question about timescales and evolution. The variations in Mars's obliquity occur over millions of years. Earth's potential variations, even in the worst-case scenarios, would also unfold over millions of years. These are the timescales on which evolution operates. Life on Earth has survived and adapted to massive environmental changes. Multiple ice ages, periods of extreme warmth, asteroid impacts, volcanic catastrophes. Evolution is remarkably effective at adapting to changing conditions, as long as those changes aren't too rapid. If Earth's obliquity gradually shifted from 25 degrees to 40 degrees over a million years, organisms would have time to adapt through natural selection. Species might migrate toward regions with more favorable climates. New species might evolve to fill niches created by changing conditions. The real threat would be if changes occurred too rapidly for evolution to keep pace. But the models don't suggest that would happen. Consider also that climate on Earth has varied dramatically, even with stable obliquity. During the Cretaceous period, 100 million years ago, Earth had no permanent ice caps. Palm trees grew in the Arctic. During ice ages as recent as 20,000 years ago, massive ice sheets covered much of North America and Europe. Life survived both extremes. We can also look at other planets and moons for perspective. Venus has virtually no axial tilt, just 2.6 degrees, and rotates extremely slowly in the opposite direction from most planets. It has no large moon. Yet, while Venus is certainly inhospitable now due to its runaway greenhouse effect, with surface temperatures hot enough to melt lead, this is primarily because of its dense carbon dioxide atmosphere, not its lack of axial tilt variation. Early Venus, when it was cooler and might have had oceans, could potentially have been habitable despite having no large moon. Titan, Saturn's largest moon, has a thick atmosphere, lakes of liquid methane, and complex organic chemistry, all without any moon of its own. To stabilize it, Titan is itself a moon of Saturn, and Saturn provides some stabilizing influence, but the dynamics are quite different from the Earth-Moon system. The bottom line is this: the Moon probably does help stabilize Earth's axial tilt to some degree, reducing the magnitude of variations compared to what might occur otherwise. This stability has likely made Earth's climate more predictable over geological timescales, which probably benefited the evolution of complex life. But it's far from clear that the Moon is absolutely essential. Earth without the Moon would experience more obliquity variation, but probably not the catastrophic swings once predicted. And even with significant variation, life is adaptable enough that it might well have evolved anyway, perhaps taking different forms or following different evolutionary paths. This is a great example of how scientific understanding evolves. The early models that suggested catastrophic instability were important. They got scientists thinking about the problem. But as models improved and more factors were considered, the picture became more nuanced. The Moon is helpful, but probably not absolutely necessary. That's a more subtle conclusion, but it's more likely to be correct. Let's talk about another crucial protective feature of Earth: our magnetic field. This is genuinely one of the most important shields protecting our planet, and some people have suggested the Moon helps maintain it. Let's see if that claim holds up. Earth's magnetic field is generated by what scientists call the geodynamo, a self-sustaining magnetic field created by convective motion of electrically conducting molten iron in Earth's outer core. Picture a vast ocean of liquid metal, heated from below and cooled from above, churning in complex patterns as Earth rotates. This motion of conducting fluid generates electric currents, which in turn create magnetic fields, which influence the fluid motion, creating a self-reinforcing cycle. It's one of nature's most elegant phenomena. This magnetic field extends tens of thousands of kilometers into space, creating a protective bubble called the magnetosphere. When the solar wind, a stream of charged particles constantly flowing from the sun, encounters this magnetosphere, most of the particles are deflected around Earth. Some get trapped in radiation belts, the Van Allen belts, and some spiral down toward the poles, creating the aurora borealis and aurora australis. But critically, the magnetosphere prevents the solar wind from directly striking our atmosphere. Why does this matter? Without magnetic protection, the solar wind would gradually strip away Earth's atmosphere over millions to billions of years. This isn't just theoretical, we can see it happening on Mars right now. Mars once had a global magnetic field, similar to Earth's. We know this because ancient Martian rocks preserve magnetic signatures from billions of years ago. But Mars is smaller than Earth, and smaller planets cool faster. Eventually, Mars's interior cooled enough that its geodynamo shut down. The magnetic field disappeared, leaving Mars exposed to the solar wind. Over billions of years, the solar wind has stripped away most of Mars's atmosphere. What was once a thicker atmosphere, possibly capable of supporting liquid water on the surface, is now just 1% as dense as Earth's. So the magnetic field is crucial. But does the moon help maintain it? Some people have suggested that tidal flexing of Earth by the moon generates heat through friction, and that this heat might contribute to maintaining the core's temperature, and thus the convective motion that drives the geodynamo. Let's examine this claim carefully. The moon's tidal forces do indeed flex Earth. Not just the oceans, the solid Earth itself bulges by about 30 centimeters twice per day as the moon orbits. This flexing does generate some heat through friction, a process called tidal dissipation. However, and this is crucial, calculations show that this tidal heating is tiny compared to other heat sources in Earth's interior. The heat generated by lunar tides amounts to perhaps a few terawatts. That sounds like a lot, but Earth's total internal heat flow is about 44 terawatts, most of which comes from radioactive decay of elements like uranium, thorium, and potassium scattered throughout Earth's interior. The additional contribution from tidal heating is less than 1% of the total. Moreover, the primary heat source driving the geodynamo isn't tidal heating or even radioactive decay. In the core, there's very little radioactive material in the iron core. Instead, it's the gradual cooling and crystallization of Earth's inner core. As the inner core slowly grows, releasing latent heat and gravitational potential energy, this heat drives convection in the liquid outer core above it. This process would continue with or without the moon. So while tidal heating exists, its contribution to maintaining Earth's magnetic field is negligible. The geodynamo is powered by Earth's own internal heat and the cooling of the core processes that are independent of the moon. This is one area where the moon simply doesn't play a significant protective role. Earth's magnetic field, one of our most important shields, would be essentially the same with or without the moon orbiting above us. Now, before we move to our thought experiment about an Earth without the moon, let's briefly touch on a few other lunar effects worth mentioning. The moon has slowed Earth's rotation dramatically since its formation. When the moon first formed 4.5 billion years ago, Earth was spinning much faster. with days lasting only 6 to 8 hours. The tidal friction between Earth and the Moon has acted as a brake, gradually slowing our planet's rotation over billions of years. Today, a day is 24 hours long. During the time of the dinosaurs, 100 million years ago, a day was perhaps 23 hours. Going back 600 million years ago, to the dawn of complex life, a day was probably 21 to 22 hours. This slowing continues today. Each century, Earth's day lengthens by about 1.7 milliseconds. That's imperceptible on human timescales, but over millions of years, it adds up significantly. Some scientists have speculated that longer days might have been beneficial for life's evolution. The argument goes that shorter days mean more rapid temperature swings between day and night, creating harsher conditions. A 6-hour day would mean the surface heated and cooled much more rapidly than with our current 24-hour cycle. However, it's not clear this made a crucial difference. Many organisms are more affected by seasonal variations than daily ones, and life has evolved to thrive under many different day-night cycles. In polar regions, organisms deal with months of continuous daylight or darkness. In caves, organisms live in perpetual darkness. Life adapts. If Earth still had 6-hour days, organisms would simply have evolved different circadian rhythms and different thermal adaptations. The climate and weather would certainly be different. Faster rotation affects atmospheric circulation through the Coriolis effect, but whether this would prevent life from evolving is unclear. Looking to the future, the tidal interaction will continue. The Moon will keep receding at about 3.8 centimeters per year, and Earth's rotation will keep slowing. In about 50 billion years, long after the Sun has died, this process would theoretically reach equilibrium with Earth and Moon tidally locked to each other, each showing only one face to the other, with an Earth day lasting about 47 current days. Of course, this will never actually happen. In about 5 billion years, the Sun will expand into a red giant, potentially engulfing both Earth and Moon. But it's fascinating to extrapolate the gravitational forces that have been shaping our world for billions of years. Now let's engage in a grand thought experiment. What if Earth had never had a moon? What would our world be like? This is where we can synthesize everything we've learned and really visualize the differences. Let's start with the most obvious change. Our nights would be darker, much darker. We're so accustomed to moonlight that we rarely think about how remarkable it is. On a clear night, with a full moon, you can walk outside and see reasonably well without a flashlight. You can read, if your eyes are good and the text is large. The moon can cast shadows. All of this comes from sunlight reflecting off the moon's surface. The moon is actually quite dark, reflecting only about 12% of the light that hits it, but it's large and close enough to provide significant illumination. Without the moon, our nights would be illuminated only by starlight. On a clear night far from city lights, you'd see the glorious band of the Milky Way stretching across the sky. Countless stars scattered like diamond dust. It would be beautiful, but it would also be dark. Walking around without artificial light would be genuinely difficult. Many nocturnal animals have evolved to exploit moonlight. Wolves are more active during full moons, when hunting is easier. Lions hunt more successfully on dark nights, when their prey can't see them coming. Sea turtle hatchlings orient toward the brightest horizon, usually the moon's reflection on the ocean, to find their way to the sea. Corals, as we mentioned, coordinate their mass spawning with lunar phases. Countless other organisms use the lunar cycle as a timing mechanism. Without the moon, all of these lunar synchronized behaviors would never have evolved. Nocturnal ecology would be fundamentally different. Some species might never have evolved at all. Others would have evolved different strategies. Bioluminescence might be more common, providing organisms with their own light sources. Echolocation might have evolved in more lineages. Keen night vision would be even more crucial. The tides would be dramatically weaker. As we discussed, we'd still have solar tides, but they'd be about 46% as strong as our current combined lunar and solar tides. The difference between high and low tide would be less than half what we currently experience. Coastal ecosystems would look different. The intertidal zone would be narrower, with less vertical range of habitat types. This might support less biodiversity, though it's hard to say for certain. Species adapted to current tidal ranges would never have evolved. But different species adapted to smaller tidal ranges would have taken their place. Tidal mixing of nutrients would be reduced, potentially making coastal oceans slightly less productive. The transition of life from sea to land might have taken longer without the strong selective pressure of large tidal zones. But solar tides would still provide that pressure to some degree. Earth's rotation would be faster. Without the moon's tidal braking, Earth might still be spinning at something close to its original rate, giving us days of perhaps 6 to 8 hours instead of 24 hours. This would have profound effects. Atmospheric circulation would be dramatically different. The Coriolis effect, which deflects moving air and water due to Earth's rotation, would be much stronger with faster rotation. Hurricanes would be more numerous and perhaps more intense. The jet streams that guide weather systems would be different. The pattern of prevailing winds would be altered. Ocean currents would also be different. The major ocean gyres, the Gulf Stream, the Kuroshio Current, and others are shaped by wind patterns and the Coriolis effect. With different winds and stronger Coriolis effects, these currents would follow different paths, redistributing heat around the planet differently. Temperature swings between day and night would be more rapid with 6-hour days. However, oceans and atmosphere provide thermal inertia. They don't heat and cool instantly, so the effect might be less dramatic than you'd initially think. Still, climate would certainly be different. Organisms would have evolved different circadian rhythms adapted to 6-hour days. Perhaps there would be multiple activity periods per 24-hour period. Animals might sleep and wake several times in what we currently consider a single day. Plants might have different photosynthetic strategies. Earth's axial tilt might vary more over geological timescales, perhaps between 10 and 50 degrees, instead of the relatively stable 22 to 24.5 degrees we currently experience. This would make climate less predictable over millions of years. Ice ages might come and go in different patterns. Ecosystems would need to adapt to more variable conditions over deep time. However, as we discussed, these changes would unfold over millions of years, giving evolution time to work. Life might look different, but it would probably still thrive. Here's something that might surprise you. We wouldn't have total solar eclipses, at least not the spectacular kind we get to witness. The moon happens to be about 400 times smaller than the sun in diameter, but also about 400 times closer to Earth, making them appear almost exactly the same size in our sky. This cosmic coincidence means the moon can perfectly cover the sun during a total eclipse, revealing the sun's corona in all its glory. Total solar eclipses have been scientifically valuable. They allowed astronomers to study the sun's corona and helped confirm Einstein's general theory of relativity in 1919 when starlight was observed bending around the sun during an eclipse. They're also among the most awe-inspiring natural phenomena anyone can witness. On a moonless Earth, we'd never experience this. We might still see Venus or Mercury transit across the sun's face, tiny black dots crossing the solar disk, but these are much less dramatic. Culturally, human civilization would be completely different. The moon has shaped human culture, religion, calendars, mythology, and language since the beginning of recorded history. Most ancient calendars were lunar or lunisolar, based on the moon's 29.5-day cycle of phases. The words month and Monday derive from moon. Countless religions and mythologies feature the moon prominently, from Selene and Artemis in Greek mythology to Chang'e in Chinese mythology, from Islamic lunar calendars to Jewish celebrations timed to lunar phases. Without the moon, we would have developed entirely different timekeeping systems, probably based purely on the sun and stars. Our cultural references, our poetry, our art would all be different. Romeo wouldn't have compared Juliet to the moon. Beethoven wouldn't have composed his Moonlight Sonata. The Apollo program would never have happened. Humanity's first steps on another world would have been to Mars or Venus instead. The development of science itself might have been different. Ancient astronomers were fascinated by the moon's motion and phases, and working out the geometry of the sun. Earth-Moon system helped develop early mathematical astronomy. Without the moon to study, astronomy might have developed differently, though probably not fundamentally, so the planets would still have been there to observe and puzzle over. But here's the crucial question we've been building toward throughout this entire video. Would intelligent life have evolved on a moonless Earth? Based on everything we've examined, the honest answer is yes, probably. While the moon has influenced Earth's evolution in various ways, shaping our tides, slowing our rotation, providing some obliquity, stability, intercepting a small fraction of asteroids. None of these influences appear to be absolutely essential for life, or even for complex, intelligent life to arise. The moon has made Earth what it is, but a moonless Earth would still have had a protective atmosphere, a strong magnetic field independent of the moon, liquid water, plate tectonics, providing geological recycling, and moderate solar radiation from a stable sunday. These are the factors that really matter for habitability. Life is remarkably resilient and adaptable. It has survived and thrived through massive changes in Earth's environment over billions of years. The differences that would exist on a moonless Earth, weaker tides, faster rotation, potentially more variable